So hi everyone, and welcome to the first Tech Talks here in Chicago. By the way, before we get started, for the folks on this side, or especially on this side, if we start like moving in a little bit and block the screen, just gesture to us, and we'll move out of the way. So don't feel bad about that. And for folks on this side, we have also our screens duplicated over there, so you can, if we are blocking, you'll be able to see the screens. So once again, welcome. One of the reasons we're doing this is to sort of bring a strong tech community here in Chicago together and bring awesome technologists like yourselves together to sort of mingle, share some ideas, and share some information with one another. So that said, just a quick introduction. My name is Hani Alamari, and I'm a software developer here at Thoughtworks. I've been with Thoughtworks for about a couple of years now, and I've been fortunate enough to work on multiple large-scale software projects that are really exciting, really interesting, and really challenging in nature, which, one of the projects that we'll share information about today with you all is all about using machine learning to detect credit card fraud at a global financial institution. And aside from project work, I've also been very fortunate to work with lots of really passionate and awesome technologists like Sarah LeBlanc. And I'll let Sarah introduce herself and give us a little bit more context and history on basically our working relationship with this client.
Yeah, so my name is Sarah LeBlanc. I'm also a developer over at Thoughtworks. I've been here for a few years. I spent the past 2 years at one of our largest clients, which is the global financial institution that Hani mentioned. Thoughtworks has had a relationship with this client for the past about 3 years. It was one of our largest clients, and we've had hundreds of Thoughtworkers work with them, both teams in the US as well as teams around the world for our offshore teams as well. For about the past 2.5 years, we've been helping them build a new platform, and the first product on that platform, which was to introduce consumer loans to this institution. This was a really interesting project with interesting technology. We ended up creating a really large system, event-based driven, as well as doing CQRS. So that had a lot of really interesting technical problems as well. Then about 6 months ago, the client came to us with a problem in an entirely different aspect of their business, and that was to help improve their fraud detection for credit card application.
Yeah, so as Sarah mentioned, basically we wanted to improve their credit card fraud detection, and for our client, or for this bank, improving credit card fraud detection meant two different things. One was improving the accuracy of their machine learning algorithms, also known as models. And then two was improving the speed in which they can make changes to these models and actually deploy them to production to keep up with fraudsters. So much like hackers, fraudsters are constantly changing behavior. And we're seeing this based on the data that we have. We have data that goes back to 2013 and 2014. And we can see the patterns in the data, and we can see the fraud trends in the data are changing year over year. So there are many different types of credit card fraud. One is transaction fraud, when somebody uses a credit card. The other is credit card application fraud, when someone steals another's identity to apply for a credit card. And then another one is card not found or card not received fraud, in which your mail might get intercepted and someone ends up with your credit card information. And the list goes on and on, but basically our use case that we're starting out with is credit card application fraud. And the main reason we're focusing on credit card application fraud is because it has less strenuous software requirements than something like transaction fraud. So if you think about it, obviously you apply for a credit card a lot less than you use one. So typically you're not dealing with the volume of transactions that you would be dealing with if you were to handle transaction fraud. Are we good with
It was causing a delay on that side.
Okay, I see. Cool. The other thing about transaction fraud is that you need to be able to validate a transaction within 10 milliseconds or less. So we obviously didn't want to, start with these stringent requirements, but we wanted to start with something a little bit easier of a use case and then expand into all of these different use cases. Now, credit card application fraud is actually quite rare. It happens in about less than 1% of the time of the credit card applications. But each time it happens, there are thousands of dollars that are lost, so there is an immediate financial impact to the bank or to our client. And if we take a look at a typical plot for a model or a machine learning algorithm, you'll end up seeing things that look like this. At the x-axis, you have a model score, and the model score is basically just a probability between 0 and 1. The higher the probability, the more likelihood that you have a fraudulent application. The lower the probability, the less likely the case. And if we were to plot the data, you'll end up with something that looks like this. So at lower scores, you have a higher number of good applications that were marked as not fraud. And then at higher scores, on the other hand, you have also a higher number of applications that were marked as fraud. Now, if our client was to threshold, let's say somewhere in the middle, so somewhere around 0.5, then that means that everything to the right is treated as fraud, everything to the left is treated as not fraud. So what ends up happening here is that the area under this curve becomes our false positive, or basically the number of applications, the number of good applications that we mark as fraud. And potentially, we may have impacted customer experience. We may have frustrated the customer, and they just said, you know what, I'm just going to leave and apply for a credit card with a different bank. Now, the area under this other curve is your false negative. And the false negative right here is basically the number of fraudulent applications that you missed. And this obviously has a much more direct financial impact to our financial institution. Now, the bank can take a look at a plot like this, and then they can start playing around with this threshold. And they do that to basically find the area where they can minimize the overall number of false positive and perhaps increase or decrease also the number of false negatives so that they can increase the accuracy of their model. So in order to come up with these numbers that minimize the financial impact, we can take a look at a formula that looks something like this. So the bank can start plugging in numbers in this formula, and what we have here is the fraud cost. And obviously the bank can take a look at an average, on average, how much does fraud cost me as a bank, and then they can plug in this number. Then they multiply it by the number or multiply it by the false negatives or the false negative rate, or the number of fraudulent applications that they actually missed. And if they add that to the opportunity cost of losing a customer, and here's the tricky bit, is that this number is not always easy to calculate. It's not always easy to add a dollar figure on the opportunity cost. But if they're able to do it, then they can multiply the opportunity cost by the number of false positives or the mistakenly fraudulent applications.
Yeah, so clearly having fraudulent applications has a direct impact on its client and on our client and its customers. So clearly it's important to have a good fraud detection system in place. So we'll start with looking at the current state of what our client was doing. So on the left side of the screen is the in-house client system, and on the right is a third-party vendor that they were using. So when an application comes in, it will get sent to the client's application service, who will send it to the vendor, who will make a fraud decision on whether this application is fraudulent or not. That decision will get sent back to the service, and the service will then either approve or deny this credit card application. So there's a few different steps to the fraud detection itself. And there's 3 steps to it. So the first thing that happens is the application will go through the rules. And rules are what you know. So for instance, if you know that this email or this social security number is fraudulent, the rules will catch that and say, yep, this application is fraudulent. If you can get past the rules, you'll go into the model. And this is where the intelligence really happens. So you give the application to the model and say, okay, based on applications you've seen in the past, what is the likelihood that this one is fraudulent? the model will give back the score between 0 and 1 that Amy talked about before, and that score will get passed into the strategies. So the strategies are what the client tells the vendor, this is what I want you to do given a certain score. So an example might be, if I want to say anything 0.7 to 1, that's fraudulent, like for sure. Between 0.5 and 0.7, we're going to pen that for further investigation maybe, and anything less than that, yeah, that's okay, that's not going to be fraudulent. So these are the 3 steps that compose fraud detection.
Yeah, to add to what Sarah said, there is also an entire governance and legal process as part of this system. So for example, before you can make changes to the rules or to the model or the way the model works, you need to be able to prove that you're not actually redlining, a specific age group or that your model is not biased towards a specific location, which is a really good process to have in place. And then additionally now, anytime we want to make changes, we have to get on the vendor's backlog and we have to get on the vendor's release cycle, which is not ideal. So obviously, basically this process, this governance process, along with getting on the release cycle of the vendor can take anywhere between 1 to 2 years.
Yeah, and obviously that's not ideal. Like Amy mentioned before, fraudsters are changing all the time. So in order to change anything, to take 1 to 2 years is going to harm how effective your fraud detection is. So we'll go ahead and talk about what we're proposing instead. So like I said, there's 3 parts to this fraud detection. What our team is brought in to work on and what we'll focus on today is the model specifically. So there's 2 ways that we want to improve the model, right? We want to decrease the amount of time it takes to update the model, as well as increase how well the model is able to actually score these applications. So for that second part, for the model performance, what we're doing is introducing this idea of challenger models. So now when an application comes in, the application service will send the application to the vendor like normal, in which it'll come back with a decision, and it'll also get sent to the different challenger models. Right? So the decision is still coming from the vendor, but these challenger models are also giving scores so that you can see how are these challenger models performing with this live traffic in comparison to the one that's actually making the score that gets fed into the decision. So now let's say that one of our challenger models is in fact outperforming the model that's in the vendor right now. We don't want to rely on the model in the vendor anymore. And instead what we want to do is introduce this promotion from the challenger model to what we're calling champion model. So now this will all live inside of the client system. Now when an application comes in, the service will still go to the vendor to have the application go through the rules. If it gets past the rules, it will come back and get sent to our models. It'll get sent both to the champion model as well as all of the challenger models. The champion model will come back with the score, which will get sent back to the vendor to get filtered through the strategies. After the strategies, you'll come back with the final decision about for the customer's application. So now this really begs the question of how do you create these models and what would make one model better than the other to be worth getting promoted to be a champion?
Yeah, so basically the creating better or creating effective models is all about training. And it's all about having a much more effective training process before you can create that model. And the problem that we're dealing with here in data science is something called supervised learning. And in supervised learning, what you do is that you basically provide your model with all the inputs and also the target variable of whether it was confirmed, an application was confirmed as fraud or not fraud. So you just feed it all the questions and answers, if you will. And then the model makes a classification. And in this case, we're interested in a binary classification because we're interested in 2 probabilities. The probability that an application was marked as fraud or a probability that it was marked as not fraud. So this is binary classification. Now, there are tons of frameworks out there that can actually train a model and read data and train a model in as little as 10 or 20 lines of code. So someone might ask, well, what do data scientists actually do then, if we can do this pretty easily? To answer this question, we need to look at some of the things or some of the workflow that the data scientists go through. So data scientists really look into the raw data and try to identify patterns within data, and then go through some data munging techniques to actually have a much more effective training process. So let's talk about some of this data munging techniques that data scientists go through. So the first thing that we'll cover is data filtering. And we want to filter data based on cardinality. And cardinality is essentially how many unique values you have within a set. So if you have data that has a cardinality of 1, which essentially means that you have just a column with one unique value across all the applications. Obviously, this is not very useful to the model because there is no variation. The model cannot really learn from just a single value. So in this case, you're just better off dropping this column altogether before you feed it the model or before you start the training process. Now, the inverse of that is also true. So if you have data that has a very high cardinality, so fields like first names and street addresses tend to have a very high cardinality because, again, you have like almost unique first names across all applications that you get. This also causes a lot of noise and slows down the training process. And what ends up happening if you train your model based on this type of data is that your model will become very good at the data that it knows, but any other piece of new information that the model gets, then the model is not as effective in scoring, basically new data. So you're also better off at, getting rid of data that has a very high cardinality. So what you really want is something in the middle, right? That's about the sweet spot. You want to be able to group data together so that you can start the training process, and then the model can actually start identifying these patterns within the data, and then the model can end up providing better predictions for you. So that's data filtering in a nutshell. Now, if we take a look at another example that also has the same problem of high cardinality is email address, right? So again, across all applications, you probably almost have all unique email addresses. But in this case, maybe you don't want to get rid of the email address because there might be some patterns here that you can benefit from. So what you really want to do here is that you want to transform this data and get rid of everything but keep the domain name. And now you actually can start seeing patterns in this data. And as you can see, fraudster.com here tends to be fraudulent application. So the model can see this data and start learning from it. Another technique is called data imputing or imputing strategies. And imputing strategies are all about handling missing data. So let's say your model was trained on something like annual income, right? The annual income of the applicant. And somehow you got an application that didn't have annual income as part of it. So now what do? Do you leave it blank? Do you zero it out? Or do you sort of average all the annual incomes that you've seen before and then you add a default value? So depending on what strategy you go with, you might actually have different effectiveness for the model. So sometimes it is appropriate to just like blank fields out or just zero fields out. Other times it is more effective to actually consider an averaging strategy for imputing. And then last but not least, there is also deriving features, looking at the patterns and the data and basically coming up with features that can benefit the model directly. And one of the features that we came up with in our project is the proximity of the IP address of the applicant to the zip code that they mentioned on their application. So if you have someone applying from Cairo, Egypt, a fraudster applying from Cairo, Egypt, and all people from Cairo are fraudsters. I'm one of them, by the way. So if someone is applying from Cairo, Egypt, and they specify basically a zip code of Chicago, Illinois, then now you can see these patterns and say, oh, this is a long distance. Maybe you have, maybe this application, there's a higher chances that it is a fraudulent application. And there's also, obviously the case of travelers, like us here, we travel all the time, and sometimes maybe somebody applies from a different part of the world, legitimately so. But this is one of the features. There's tons of features that go into model training, and each one of these features are weighted as well.
Great, so now that we kind of have an idea of how these models are created and why some of them might perform better than the other, we'll go over now the architecture and the system we're designing to allow for this experimentation and then putting them in production. Before I get too far into this, can the back hear me okay? Am I projecting okay? Okay, just checking. So we have two workflows that we're going to go through. We have the data scientist and the developer. So the data scientist goes from having raw data to having an actual trained model. The developer workflow, will take that trained model and put it in between the applications to actually make a decision on whether those were fraudulent or not. So we'll go ahead and start with the data scientist workflow. So you start off with the raw data, which you're going to get from wherever your historical data is being stored. That will then go into the transformation code, which will do some of the things that Haney was just talking about. Because we want to promote data science independence, we want the data scientists themselves to be writing all of this code in our system. Because of that, we want this to be in a language that they're used to and comfortable with. So in our case, this is in Python. The transformed data then gets sent into H2O, which is an AI library that will take in the data that you want to test, as well as which decisioning algorithm do you want to use. H2O will then output the model as Java code, and you can think of this Java code as just a simple class with one method where you give it the data and it will output the score. So it's pretty simple idea. It will also output some useful metadata, such as what data was this model trained on, as well as accuracy analytics. We then package this into a jar file and then store it in a binary repository. So this is an overview of the data scientist workflow, going from raw data to having a trained model stored in a repository. So now we'll go over the developer workflow. Sorry, that one's a little bit of a lag. I'll make sure I get it. Yeah, okay. So we ended with these models being stored in the binary repository as jar files. What we want to do, each jar is a model, and what we want to do is service enable these models. Now basically this is just going to be a way to access that score method. So it's going to be a really lightweight service. So in our case, we're writing it in Spark Java. Basically just one endpoint to score this application. The application flow itself will continue to happen for now, but when the application service gets a new application, in addition to sending it to the vendor, it's going to send it to this decisioning and analytics platform. We might want to do some transformation on the data coming in from these applications, and since we want the data scientists to write that, this is going to be written in Tornado, which is just a simple web framework for Python. This platform will then send the application to these models, who will send a score back, and their scores will get stored in a model score repository. Now, since these models that we've service enabled are not actually giving the score that's used in the strategies to make the decision, we're deploying them in what we're calling shadow mode for now. What this allows for is the fraud strategy team can now look at how are these models deployed in shadow mode performing against the model that's stored with our vendor. So let's say that they find one that's outperforming and that they want to use that score when making the decision. What this means is that we want to no longer use the model from the vendor and do this promotion from shadow mode to becoming the champion. So now when an application comes in, the application service will send it to the vendor, like I mentioned before, to go through the rules. If it passes the rules, the application will come down to the decisioning analytics platform, which will send the application both to the champion model and to the models deployed in shadow mode. The champion model will send back the score, which will then get sent back up to the application service and over to the vendor to go through the strategy. The final decision will come back and get sent back to the customer. So now this, all what I was just saying, is a synchronous process, right? Because obviously we're waiting to hear what is the score so that we can either approve or deny based on if it's fraud or not. Meanwhile, asynchronously, these shadow mode models are also giving scores that get sent back into the store so that the fraud strategy team can continue to look to see is there any better model out there to use. So in this way, we're really introducing continuous delivery to machine learning because we're allowing these data scientists to experiment with models, deploying them to shadow mode to see how they do with live traffic, and then there's a promotion right to champion, and this will all be in-house. So this is the overarching, so that is the developer workflow, right? From getting applications in production, live traffic, to making decisions both from the champion model and from the models in shadow. So this is really an overarching picture of our architecture. Okay? Right, so from the data scientist point of view, we're allowing them to do this experimentation with creating new models, doing different data transformations, and then when they're ready, we'll put their models into shadow mode, and then when the fraud strategy team is ready, we'll put those into production to do actual scoring.
Yeah, so now that we've seen sort of the overall architecture and the overall workflow of the data scientist and the developer, let's try to tie things together in terms of our value stream or our pipeline, and also see, I mean, we talked a little bit about the governance process, but let's now see where that fits right into the picture. So as we mentioned before, we start with the data ingestion layer, which we read the data, we run these transformation or the data munging and prepare the data, and then basically now we're ready for the next step, which is model training. And when we do model training, after the training process, we store things like accuracy reports on the model. We store things like what time period the model was trained on, and basically we have a bunch of metadata that is associated with the model. And that's really when the governance process kicks in, or when the governance group comes in. And then they're interested in answering questions like who trained the model, what time period it was trained on, what time period it was validated on, and also they're interested in an overall explainability of the model. So how did the model arrive at a certain decision? And what features were taken into account to actually arrive at a certain prediction? So that's when the governance group comes in, and when they're happy with data that we have or with all the reporting, then at this point we are ready, we get to go ahead, we're ready to publish our model into a binary repository, something like Artifactory or Nexus. And then as Sarah mentioned, we take this model and we service enable it. So we take basically that model service and we also publish it into a binary repository. And now we're ready for the deployment process into what we call shadow mode. So now we can, the fraud strategy team can take a look at the different models in shadow mode, and they can decide on the model that is outperforming all of the other ones, and the model that's outperforming the current champion model. And then they say, okay, we're ready, for this to become the champion model. Let's go ahead and have a final review by the governance group. And you might be thinking, okay, like why are we doing this twice for the governance? Because really, when you put stuff into shadow mode, it doesn't necessarily make an active decision. It's just logging data. But here, the governance, the final governance evaluation is really important because you're making the active decision. So at this point, the governance evaluation or the governance group says, okay, go ahead, and we can start deploying this model to become the champion model. So from this pipeline or from this value stream, you're not really seeing anything credit card application fraud specific in this picture. So we can technically expand this to other fraud use cases as well. And actually, we can move outside of fraud completely and deploy other machine learning models by using this value stream or by using this pipeline. For instance, our bank can deploy models to come up with pricing strategies for loans or for credit cards. So let's say a customer applies, and based on things like their annual income, their credit history, they can come up with an interest rate for this particular customer. And beyond this use case, you can also use it for things like behavior and analytics. So you can evaluate basically your customer's transaction behavior, and if some of your customers are basically travelers, or they dine out a lot, then you can develop a machine learning model that can basically advertise credit cards that will help them with points, or a much better reward system than they have. So really what we're trying to deliver here is a machine learning platform as a service, and not necessarily something that is specific to fraud or application fraud. This is just a use case that we're starting out with.
Yeah, and so it's been a pretty interesting project to be on so far. So like we said in the introduction, Haney and I are still on this team, which means this is still in progress. But it's been a really interesting problem so far. We still have some of this to still figure out in full detail. But there's been a lot of learnings. Like one, for example, is that neither Haney nor I are actually data scientists, right? So we get
data scientists.
Or fraudsters, yeah. So getting to learn from the data scientists on our team has been a really, really cool experience. But yeah, so it's been a lot of fun. So we're open to any questions. But yeah, thanks for coming. Yeah.
Can you give us a sense of the timescale between when an application is approved to when you actually detect that there's fraud? It seems like that would be quite a bit. And then similarly, what's the lag time between like a shadow being promoted into production to the champion?
Yeah, so I'm going to repeat the question just to make sure I got it. So what is the timeline between when you get an application and you officially know that it's fraudulent, as well as the time scale between putting a model into shadow mode and then promoting it to production? So I can take the first part of that question. So you have like a 6-month window between when you get an application and when it's confirmed fraudulent or not. So that kind of will also give you an idea, right? You can't tell if a model in shadow mode is outperforming or not until you get that final decision for the live traffic. But there's like about a 6-month window in there.
Yeah. And then your second question was how long it takes for
how long
shadow
does something last in shadow mode?
Yeah, so that's an interesting question. So as Sarah mentioned, we're still sort of like 2 months in this project, and we're just about to deploy the first model into shadow mode. So we're kind of trying to figure out this process as we go with the governance group. So we still haven't defined it quite yet. They have to be comfortable, obviously, with with the data being there for some time, having shadow mode score these applications for some time. And we're already seeing, in terms of model accuracy, we're already seeing a much higher accuracy from our model than the vendor. So that's good news, but we still want to run it in production against live traffic and see how it is arriving at the decisions. So it will also feed into the answer that Sarah did, which is sort of going to be like 6 months. Yeah, it's probably going to be around the 6 months mark, and a lot of that is also due to politics, like at the bank as well. So, which if you work at a financial institution, you're sort of familiar with that. Yeah.
Do you have a strategy for how to introduce different shadow models into the system over time, which are going to become champions over time?
So the question was, do we have a strategy for how we're going to introduce shadow models or models into shadow mode and then pick champion models?
There's different shadow models because you have there's a shadow model, and then data scientists are taking them and figuring out, it's a different model. It's different model. Then you have two methods, right?
Yeah.
And you pick and choose maybe it should be because they're outperformers. The vendor says, right?
Yeah, so that's a good question. So let me maybe try to dig in a little bit deeper. So is it do you mean we have, let's say, 2 or 3 models, and 2 of the models are one is better at something, the other is better at something else? How do we reconcile these things and promote something?
Let's say personally think, okay, let's start with one model, see how that works. Fares against the vendor
Yeah.
data. And then over time, the data science team said, well, we're going to have that one model, shadow mode, but we just came up with a whole new other model we'd like to introduce. So to see how things compare over time and so on. And maybe the next day after, one of them brings up a whole new model, to say, hey, let's add a third one and so on. Is there a strategy for how that works, or is it extensible case?
Yeah, so you can have multiple models in shadow mode running at the same time, right? They'll all be scoring back to the prediction store. That will then be like getting compared to as well. One way that we're thinking about like the scalability for that portion of it, right, is if you have 6 models in shadow mode, it's not ideal, right, for that platform to have to know every model that's deployed in shadow mode, right? So one way that we were thinking about dealing with this in the future when we get there is to have a queue in between, right? So the platform will just send those applications onto the queue, and any model deployed in shadow mode will know that queue and they can pick up applications as they go.
The original reason for the question is when the presentation started, we mentioned that Fraudsters come up with different ways of
Yeah.
Right.
gaming the system. So,
Yeah.
so it's good to have newer models that are possible.
Yeah. Yeah, and that actually happens, like that happens all the time, or sometimes we pick up like one of the models that are, that have been published before and maybe like, run some tuning on that model and then publish a new version of that model. It's still based on, the same algorithm, the same machine learning algorithm, but maybe we introduced a new feature to this model, or maybe we just like, tune the model a little bit and then we deploy. So there is no limitation on how many models, as Sarah mentioned, that you can deploy in Java.
I like the ambition of the machine learning as a service kind of thing. What other use cases were you kind of thinking about, like outside of this application, like what other companies would come to apply that model?
So we're already, Uber, I believe, published an article recently about a platform that they're building that is sort of similar to this. And it's also just a generic machine learning as a platform, or machine learning platform as a service, in which they can basically identify the wait time for Uber Eats. And so far they're seeing success with it. So you can really do anything. You can deploy unsupervised learning machine learning algorithms. In which case you're not interested in a classification, but you're interested in like getting a bunch of data and then clustering that data. And if you're familiar with Google News, what they do is basically they add like a headlines, but then they ingest a bunch of different articles and then cluster these articles under the same headline. So that would be an example of unsupervised machine learning. So again, this platform is not just specific to supervised learning, but it could be used for anything that doesn't require human intervention. Yeah, back there.
Yeah, just interesting.
And then we'll come to you. Sorry.
Are you also monitoring false denials at the same time? Because it's similar to spam scoring. Like, we can get so good when you start blocking stuff. You shouldn't.
So the false denials, maybe we can go to one of the ROC curve gets. If we go to one of our, there we go. So one of the plots that we have, or one of the charts that we produce as part of the model training is an accuracy plot, and this is called the ROC curve. So the ROC curve is basically a way where you can know where to threshold, right? So at higher points, you're going to have like a pretty good accuracy of your model, close to 90% accuracy. But what that means is that you're also tied to a specific false positive rate.
This is acceptable.
It is an acceptable risk. Yeah, you will never be able to have a model that arrives at 100% accuracy. But this is basically what you can arrive at to say this is the risk that we're willing to take. And at each point of this ROC curve, it corresponds to a false positive rate.
So after you, we can come to this side now.
Sure, so I had a bit of a two-part question. So the first is, when you deploy these models in Shadow, are they effectively static and fixed at that point, or are they continuing to learn from the live data? And then the second was about the strategy team that reviews performance of the models. Have you considered the possibility of humans accidentally selecting a model that performed great over a certain center at a time? You know, it's 100% accuracy, but it's actually just a really overfit model. And once you deploy it as a champion, horribly. Do you have anything to sort of control that?
Yeah. Sorry, can you repeat the first question? I had an answer to it, and then I forgot what the
Sorry, I
question
have like 9 questions.
No.
I tried to limit it to 2.
Can you repeat the first one?
Sure, so the first is, once you deploy the model in
Yeah.
Shadow,
Oh, yes, yes,
is it
okay.
continuing to learn from the data, or is it just a static set of rules of that?
Yeah, so right now, by the time you get in shadow mode, you're like done learning for right now, right? So you had the data scientist workflow at the beginning, and that's where you do the training using H2O. For our current system, when you're in shadow mode, like you're done learning. I think it is a goal in the future to do online training as well once it's in there, but that's more towards the future.
Yeah, so offline training for now, and also like in order to use H2O in higher environments, that requires different types of licensing and like things like that. So it takes a little bit again, like with financial institutions to get this sort of stuff together, and then we do have plans, as Sarah mentioned, to do online training in the future.
Okay. And then with the supervisory group, like what criteria do they use to decide what model, and how do you make sure they're not picking a model which is very overfit with your
That's a good question. I don't know the answer to this question yet. Yeah, I don't know. I mean, yeah, that's an interesting question.
I'm sure we'll like come to that when we eventually like have one in shadow mode that we want to, yeah.
Yeah.
But right now, it's just a question.
You said online, where you mean live data analysis?
Yeah. So in that case, it would be you have these models in shadow mode, and you have this live traffic of applications getting fed to them. Currently, they're not learning from those live ones, but in the future. Can we get someone from over here? Yeah.
Can you share an interesting piece of data that machine learning discovered about fraudsters? So like, you gave the example of the zip code and the IP. Can you give one that's like one that you wouldn't figure out by yourself?
Are we allowed to?
I'm trying to. I can think of a few.
That's a dangerous question.
Yeah, I don't know.
Yeah, I think. Yeah, like the other use cases will give too much.
And how did machine learning find it? Like I'd like to learn like, so how did was that the data scientist saying, if we take their last name and their date of birth and put it together, we can figure out fraud, or is there a what learned that? Like let's say last name and date of birth, it was an indicator.
Mm-hmm.
What is the data scientist putting that together, or is machine learning putting it together? And then what is that machine learning if that's the answer?
Yeah, so one thing I've seen is that it is in big part the data scientists, and it's part of that data transformation at the beginning, right? So it's which ones are useful or not, what do you do when you don't have a field, especially the feature selection is really interesting, because that's kind of like what you mentioned, right? Looking at patterns in what exists. So from what I've seen so far, it's a lot of the data scientists.
Yeah, it's an interesting question, and there are like lots of different use cases, but it's really hard to share because it gives a bit too much, like insight into how the model like makes decisions. Yeah.
How did you decide to use the H2O learning on IDs and which one were the ones that you evaluated, and what were the pros and cons?
Yeah, that's a good question. So our client is JVM heavy, JVM-based applications. That most of their applications that are deployed in production are JVM-based. And H2O, like one of the abilities that it has is that it takes a Python model and actually converts it, right here, converts it into Java code that represents, basically it's a stateless class that represents, like the different decisions that the model can take.
So it was dictated by the infrastructure?
It was mainly by the infrastructure. Yeah. Unfortunate, but true. Yeah.
Now, it's H2O, they're developing reasoning. They're developing a system that shows why it shouldn't work. That's a lot of it.
They are
Developing a system that shows the reason behind why it shouldn't work.
yeah, so the question was, does H2O sort of provide an explainability of how the model arrived at a certain conclusion? To a certain extent. A lot of these models, in a way, are kind of like a black box, but to a certain extent, not as like as much as we would hope, but to a certain extent. And initially, we started with a framework like scikit-learns, and because of the deployment infrastructure, we had to switch to something like H2O. Yeah.
So, you guys consider what strategy you use as you launch as far as collecting enough metadata in order to justify the decisions you made, the time you made them, the model you made them, things like discovery and lawsuits, because when you're trying to champion, it's going to make decisions, and someone's going to ask you, why did you make that decision? What was the data? What was the model? What's your strategy? That's a ton of data to continually have.
That's a great question.
That's a great question, and I'm sure our strategy team has an answer. We're doing the heavy lifting of the platform, so unfortunately, I don't have like insight into that whole process. But
Do you kick off a lot of metadata though, or is the model kind of making a decision and then that's it? It doesn't get attached with like what are we trying to do with the model? Are you kicking off metadata, or is that another system that's trying to collect that metadata after that?
So we are kicking off metadata as part of the training process. So for example, things like what year the model was trained on. And then there's also validation process that we haven't really gotten into, which is essentially you train the model on 1 year or one data set and you validate it on maybe another data set or the same data set, but you don't give it the answers. You don't give it what's fraud and what's not fraud. So we provide all of this metadata during training, and metadata such as accuracy and things like that. And then the other data that we provide is just the data that's provided in the prediction store. But beyond that, we don't provide anything else. We'll take a question maybe from back there, and then we'll go to you.
I have a follow-up question from the IR speaker.
Yeah.
In your historical data, obviously, false positives fraud, making something else. False negatives being visible historically. So when you're looking at the IR speaker, you're looking at what's being labeled in the historical data. Do you have any way of going back to the historical data and kind of removing that pre-existing bias of the false positives? We denied someone, but could have been like, what?
So the question is, if we denied an application that turns out to be a good application?
Yeah, how do you figure that out so that your historical data can include that, and you're not just looking at what previous models have labeled the application?
Yeah, so that's a really interesting question, and so sometimes you deny someone an application where it is a good application, but there is some sort of a human intervention sometimes where you deny an application, but then you follow up with the customer, right? And that's typically like the fraud strategy team or some of their operators at the bank. They follow up with the customer, and sometimes you get basically no response. So when you get no response, that could mean one of two things, right? One, that this person is really fraudulent, right? The other could mean that you have frustrated the customer, right? And they just didn't, they said, I don't care, I'm just going somewhere else. So that's a little bit hard to quantify. And then I think back there you had a question.
Yeah, is there anything you're doing to ensure models are not usable? Like, so a model could be identified itself 99%, but then let's say it has kind of old, then fraudsters might be figured out. So this field, this way, they all. Is there any kind of way you have to guard yourself against that?
Yeah, so what we're dealing with is around 300 to 400 variables that can determine whether an application is fraudulent or not. So just one field wouldn't make a ton of a difference. Obviously, a bunch of different fields would. And also the other thing to kind of like look at is the feature importance, right? So basically the IP to zip code proximity feature is, does have a feature importance along with a bunch of other features that we have. And these features tend to be weighted. So, the model will be biased towards more of the, like the features that are more important than other features. But you're still dealing with a bunch of different variables.
But you still have, they have the opportunity to figure out I use one example.
Right.
They obviously have to say, put a unit and gauge the model and your model.
They can create a model against our model.
Fine. The only question is, if you feel they can't make it,
Yeah.
then that's it. But
Yeah, and I'm sure that can happen, right? There is a certain level of accuracy that the model will be able to respond with, and there are other cases where I'm sure fraudulent applications will slip through. But the thing is, how do we minimize that? How do we minimize that like overall?
Okay, we have time for one more question.
Does the vendor, so the vendor did a check before they sent the data to your model? Do they change those rules often? And if they do, how does it affect your model?
Yeah, that's a great question too. So like I mentioned before, right, it can be an issue to update any rules, models, or strategies currently because they all live in the model. What I forgot to mention is that there are other solutions in place to also bring those in-house as well. How would they affect the model was your question? How would the rules?
Yeah, since, it would mean that the characteristics of the set of applications that you're actually seeing is going to change.
So that would go back, I think, to the question of online versus offline training. That would be a really interesting question when we're doing online training. So the question was, if you're getting these applications filtered out by the rules that they don't pass, you're missing out on a bunch of fraudulent applications for the model to be trained on. So that's a great question, and that would probably be very pertinent for online training. For our case of offline training, I don't think it would make as much of a difference. Okay, so we got called on time.
Yeah, let's go back real quick. One quick thing that we wanted to mention is the upcoming TED Talk. So one of our own, Anastasia, is going to be presenting on modeling complex domains biopharma case study, which is the current project that she's working on. And that's going to be November 9th. And it's going to be on meetup.com as well, so be sure to check it out and sign up for it, and we'll have another awesome get-together like this one again.
Yeah, thank you all again.